But I'm only there Tuesdays and Wednesdays. Guarantees it's Tuesday. It's like Jenna and myself. That's always very good in the mornings. Like it's like guaranteed I'm gonna show up. They'll just like sit there. Yeah. I'm already like she like didn't confirm it and I'm like my roommate, yeah, like why am I trying to watch it? I love this. I'm very it's absurd. The first nights are always it's just like uncomfortable to watch, but also like super fun to watch. My mom was like,
oh yeah.
I mean, sometimes but like I mean, compared to what the other like games feel, then you like will see why.
All right. All right, so here we are on the 30th of May. Almost done with May. June starts pretty soon here. Note that we have no assignment today. And then we do have an assignment on Monday. So that'll be hopefully clear by the time we get done today what's going to happen with that. And so, yeah, I had a really good weekend. My son-in-law and daughter and 2 grandchildren are here. Had a good time with them. One of my daughters is getting married on the 6th of July, so they had the bridal shower, and we went to the mall, so that was good. So since I really don't have to do anything, I don't anticipate my schedule to be affected by the wedding at all. All I have to do is walk just a few feet. I do have to get some clothes, wedding appropriate clothes, but I think that'll work. Although one thing is happening, I'm starting to teach an online class beginning this coming Monday, which will be an 8-week class. So that'll probably put some demands on my time, but hopefully I'll be able to keep all the plates spinning. And yes, you can let me know if you have any questions on this next section. But because of the weekend and everything, I will not be grading your tests until tomorrow, and I will post your grades on Friday, so you'll know where you stand. And those grades will not be posted on Blackboard. They will be on the textbook publisher site. You have the different assignments that you do. One of those assignments is test number 1. Well, that's where I get to post your grade for test number 1, okay? And so you'll see that hopefully on Friday, and that'll be all set, most likely. So any questions about the schedule at all? Okay, so hopefully you are aware that the notes for each section are available on Blackboard. And so we're looking here at these notes, which are in chapter 4. And so we're going to go through all this. And this is part of, if you might want to say, getting us out of your comfort zone with regards to statistics and what it's all about. So, I already mentioned this, but today is the day we're going to go into more detail about it, and that is the question of things that we don't really know, which is also known as probability. And in order to understand probability, we have to kind of go back a little bit and talk about our purpose. Okay? What is the purpose of statistics? Somebody tell me that. Answer that question.
Is it the definition of statistics?
No, the purpose of statistics. Not quite. It has to do with data, but it's not simply finding the data. That would be the definition of statistics. What I want is the purpose of statistics. Almost. We're almost there. Okay, and I'm going to ask you this question, hopefully, every time we get together, and by the next couple of weeks, you'll probably know the answer to this question without having to look it up in your notes. What is the purpose of statistics? Why are we doing statistics? What do we want to get from statistics? No, that's the process of statistics. It's not understanding the population based on a sample. Okay, so since we've had a number of wrong answers so far, let's go with the right answer, which is data-driven decisions. Okay, the purpose of statistics is data-driven decisions. I'm going to ask you this every time. Hopefully, by the time we get to the end of the course, you will remember the answer to this question. What is the purpose of statistics? Data-driven decisions. I will not ever put this on a test because I want you to know it every day, and I'm going to ask you the question every day. And hopefully you'll be able to answer this question every time I ask it. The purpose of statistics is to do data-driven decisions. Much of our world today has gone this direction. If we ask a question, where did Google come from? This. Where did Facebook come from? This. What do most hospitals do to treat patients? This. What do places like Walmart do in order to have customers? This. Why would a place like Toys R Us go away? This. Because data-driven decisions say that you don't need a store to sell toys if a lot of people are ordering online. How do you know a lot of people are ordering online? Well, they're just not coming into your store? No, because you need to know why they're not coming into your store. Are they just going somewhere else? No, they're not. They're going online. So you can't have a location to sell toys and make it profitable because you're not going to sell them. And you have data to back that up, and then you decide, okay, it's worthless for us to try to make Toys R Us a better place. It just needs to go away because people are not going to buy our stuff in our store. So we're out, we're gone. What happens if you click on a website? Google knows where you went, and it puts an advertisement on that website because of your interests. How does Google know what you like? Well, you told them when you clicked on those other things about this particular kind of fashion or sport. And so then when you click on a different website which has nothing to do with that fashion, you're going to see ads that have that fashion or sport or whatever on it because Google is making data-driven decisions. And they are making billions of dollars from this because they know something about you. The way they know that is because you clicked on something and you allowed them to know that you clicked on it. Facebook is the same way. Now, it doesn't always work, however. And in fact, it's not always the best way to know things. There are two other things that are necessary in order for you to do data-driven decisions correctly. The first thing is that you need experience. If you try to do your, let's say you're running a daycare and you want to run it the right way. If you take a survey of people to find out what they need in a daycare, you're going to have trouble if you don't have experience with surveys. We already talked about that, how the way you ask the questions can affect how people answer the questions. If you want to help middle schoolers with their anxiety problems, you probably just can't hand out a survey to middle schoolers saying, hey, do you have any problems? They probably won't respond to just a little piece of paper that asks the question, do you have problems? So you need to have experience to know how to get your data in the right way. But there's something else that you need, and that is humility. Humility is based on the fact that when we do statistics, we do not actually know what the answers are going to be. Because the numbers are always changing, so we cannot actually know what the results are going to be based on statistics. Humility is connected with probability. Probability is basically understanding things that you're not sure of. Okay? Understanding things that you're not sure about. Understanding things that you're not sure about. That's what probability is. Okay. So, how many of you have played a game in which you rolled dice in the last 6 months? Okay. There's still people out there who do that kind of thing. That's good to know. All right. So that's pretty important. Let's, well, Natasha, can you give me an example of a game you would play?
Well, most recent one was Yahtzee.
Yahtzee. Oh, that's a great one. I like Yahtzee. All right. Yahtzee. How many of you are familiar with the rules to the game Yahtzee? Not very many. Okay. Natasha, what's the best possible thing you can get in Yahtzee?
Yahtzee.
Which is what?
All the same number.
All the same number. They have all the dice come out to be the same number. Have you ever done it on one roll?
My daughter does it all the time.
Wow, that's great. She's got the touch, I guess.
I guess.
Magic touch. So you've actually seen it happen when you have all 6 dice and you roll them out and you have them all come out the same.
Me never.
You never, all right? Her, it's happened more than once. Okay. I'm going to say this to you, and I think you're going to agree with me. There's no way you can actually know what's going to happen before it happens.
I thought you were going to say just a cheater.
Oh, yeah, okay, yeah, she dropped it on the floor. Oh, no, it is the right one. Okay, yeah, put it on. Okay. If you've ever played a game that has dice in it, or a game that has cards in it, you know that you can't know what's going to happen next. As it turns out, that's the way everything happens. We don't know what's going to happen next. All right? But that's connected with the idea of humility. And we talked about this already. In order for somebody to, let's say, for example, win an election, a lot of things have to happen a certain way. And if we ask the question, is it true, and this has come out recently in the news, that there was a guy on the news who said, the only way that Trump could have won is if the Russians cheated and they gave people fake news, and people believe that fake news, and that's the only way that Trump could have won because it was such a small margin of victory in specific areas of the country. Well, I really want to go against that idea because there's a guy who worked for the Trump campaign who produced Facebook ads in those specific areas of the country the week before the election with specific issues that were devoted to specific people in order to change their minds. The Russians didn't have to do that. There was a guy on the Trump campaign whose job it was to make that happen. He did that thing. People saw those ads. They looked at those issues. They made up their mind. They voted for Trump, and he won. Now, that person did not know that was going to happen, okay? They hoped it would. A lot of the other media organizations did not think it would happen. And so they said, well, Hillary's got this thing in the bag. But she did not. And one of the websites that I looked at said that Trump had a 30% chance of winning. If Trump had a 30% chance of winning, that meant it was possible for him to win. And so what you have to work on when you're talking about humility is that you don't always know what's going to happen. In fact, truth be told, you never know 100% of the time what's going to happen. Is it possible that you could walk out of this room and go outside and there be a thunderstorm? Is it possible that it could happen in the next 20 minutes? Okay. You don't actually know if it's going to or if it's not, but it's possible that it could. Now, if I were to say, is it possible that it would start snowing? You're like, well, no, not really. Okay? Because we live in a part of the world where that's not going to happen this time of year. However, if you ask the question, could it snow in April? Yeah, well, it did. Okay. So those kinds of things can happen. And so you have these ideas of probability, knowing what things are likely to happen. Most of you prepared for the possibility that it would be raining sometime today, in the sense that it's in your mind, it could happen. So then those are the kinds of things that if you say, what about if somebody has, let's say, well, I just saw this today. What if somebody is smoking a cigarette? Does that change the probability of them living to like 95 years old? Well, yeah, it does. But you can't say to this person, you're not going to live very long because you're smoking. You don't know the answer to that question. You can say the chances are that this is going to affect your health. But you don't know that that specific person is necessarily going to be affected by that. Now, how do we actually define the formula for probability? The formula for probability is this. The number of items in a specific set divided by the total number of items. Now, what this requires from us is that we have to think about putting things into groups, okay? But this is the definition that we're going to use. The number of items in a specific set divided by the total number of items. You have to be able to count correctly in order for this to work. And it's not always easy. It looks simple, but it'll get more difficult as we go through it, okay? Now the fact is, and we talked about this also, most mathematics does not relate to this. Most of the time when you get an answer in mathematics, it's always the same answer. But in statistics, what we're talking about are things that we don't actually know for sure. So we have to think about those in a different way compared to how we would do it in regular mathematics. Now, there is something that we have to consider, though. Well, let's talk about the die first. Let's say I have a regular 6-sided die. And when we say die, most of the time this is what we're talking about, a cubic shape, right? Which has 6 sides. What is the probability of getting a 5 on it? Now, this number 5 right here is a label. This is not the letter P multiplied by the number 5. Whenever you see this thing where it has a capital P and then parentheses, this thing here is a label. So we can have things like the probability of rain, or the probability of getting the flu, or something like that. So you need to be aware of how we do these things in what's called, for those of you that have seen it before, a function. You don't have to know that word, but that's what this is. It's a function where you have the capital letter P, and then you have a label about what you're talking about. It's the probability of a thing. This is not multiplication. This is probability of getting a 5. And we say it's 1 divided by 6. All right, I want to know what the decimal is for that. What's that decimal number? So you might want to use your calculator for doing stuff like this. Okay. All right, Emily, what percent is that? It is. Now, if we were to round it off to the nearest percent, what would it be? No.
To the nearest percent? Oh,
17.
yeah, I was rounding up from where it's at right now.
All right. But it's 17%.
Yeah.
Okay? So when we say, how do I make a decimal into a percent? If I have this, and I want to make it in percent, I move it over 2 places to the right, and that's 16.666%. And then if I want to round it off to the nearest percent, it looks like this. If I say, what's the nearest 10th percent? What would that be? Yeah, 16.7%. Okay. Now your homework is going to ask you to do stuff like this. Okay. So you need to understand how to actually put these numbers into the computer. If it asks you for a decimal, it's 0.1666 repeating, and then you'll need to put a 7. You round it off like to 4 places or whatever. If it's asking you for a percent number, and then they'll ask you to round that off to the 10th percent or just the nearest percent, then that's what this looks like. Okay? So, Natasha, I'll pick on you. Let's say that you've got 4 5s, and you've got 1 die to roll. And you roll that die. What are your chances of having a 5 come up and getting that Yahtzee? Are they good? Not so good?
Be 1 out of 60?
Yeah, it would. So it would be this, 17%. So would you say it could happen?
Over 5%.
Yeah, there you go. Wow. So that's what we're looking at here. If something is less than 5%, then that would be considered unusual. So if you've got these 4 dice and you're trying to get a 5 on the last one, and you roll that die and you get a 5, you're not going to be shocked because this is more than 5%. You'll be pleasantly surprised. Okay? Chances are you'll actually not get it because it's a lower probability. But it's possible, and so you're happy if it does happen. You would certainly not be surprised if you lost, okay? But what does that mean for things that are over 95%?
It means it's usual. Anything between can happen.
Okay,
May not.
all right, so this would be what we call usual. So we don't have thunder, but we have great big machines. So close enough. So now we understand this situation, and we know that we don't know what's going to happen, right? Now I'm just gonna address something here that needs to be kind of in your mind, okay? There is a question, are there actually random events? Or are these events not just random? Some people talk about fate or karma, where it's like, well, it's going to happen a certain way because that's what karma says. Like if you kick your dog, you'll have a car accident or something like that, right? So then that would be karma. Now there is, if you want to say, a philosophical or even a theological idea where you say something like this, getting a 5 on the die, is not just random, but it's part of a divine plan that's out there. Now, it could be that it is, but generally speaking, we don't have that information. So if it is part of a divine plan, that's not communicated to us ahead of time. So it's like, if there is this big divine plan for every aspect of your life, even though that can be true, you don't know what it is. And so then, since you don't know the plan for every aspect of your life, you think about things according to the pattern of what you see happen. And again, you don't know what's going to happen, but there are certain things that might or might not happen, and you can organize your thinking in those things. Now, what are the chances, what's the probability of getting a happy face on a die when you roll? Somebody said 0. What's the probability of getting a number when you roll a die? If you say 100, it's not exactly right. You would be saying 100%, which is actually the number 1. Okay? So what this is telling us, that if we look at probability and we ask the question, what can happen here? The probability, and we write it this way, has to be between 0 and 1. Now this is really very important for you, because when you're working on a problem and it asks the question, what's the probability of this? If your answer is greater than 1, it's wrong. Or if it's a negative number, it's wrong. Probability cannot be a negative number, and probability cannot be greater than 1. Now, at the same time, we have to recognize that these things, we have to keep our humility in doing this. I have threatened various times to sneak into people's houses and paint happy faces on all their dice, right? So then if I snuck into your house and I painted happy faces on all of your dice, then it would not be 0, okay? But we have to have a little bit of reasonableness. I'm not in the business of sneaking into people's houses and painting their dice. So could it happen? Maybe it could. Could it snow this afternoon? No, I don't think so. I don't think it's possible. But there are certain situations where we say, even though it's a very small probability, it could happen. It might happen. But we just need to be reasonable about it and how that works. Okay. So then, we need to think about 3 kinds of probability. There are 3 kinds. Types of probability. The first one is called classical. Classical probability, we say that every outcome has equal chance. Is it true that if you roll a die, that everything is equal? Generally, yeah, sure. What about flipping a coin? Is it 50-50?
Yeah.
Have you ever had a coin land on its edge? It's happened to me a couple of times. I flip the coin, I miss catching it, it lands on the edge, it rolls away. So it's not actually 50-50. Other things can happen. I mean, if you were in the Old West, right, you're flipping a coin, somebody could shoot it while it was in the air, right? And there are people who actually practice so that they know what the coin's going to land when you flip it. Okay? Don't spend your time around those people. They're not. Okay? Most of the time, we think this works. However, it doesn't really work all the time in every situation. There are things that affect the probabilities, right, of different things that happen. And this is where we get to empirical or observed probability. And it's pretty simple, actually, because what we're talking about here is the number of items that we observe out of the total number of items. Okay. How many of you have had fruit juice today? 1, 2, 3, maybe. How many of you had fruit juice in the past week? 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Those would be empirical probabilities. Or I would say, what's the probability of somebody drinking fruit juice? I would say something like 9/30. If I observe 9 people, and the class is 30, what's that as a decimal?
Probability, do you break it down?
Yes. Okay. What'd you say? 0.3. Okay. What would that be percent? 30%. And then if it's 9/30 and we say, what's that fraction? We can divide top and bottom by 3, right? So it'd be 3/10. This is an example of the kind of probability that's always changing. If I say, how many people drink fruit juice in a week? If I ask a different group of people, I get a different answer. So this 30%, which I observed of the people of this class, is not the final answer. Unless I was just wanting to know for this group and for this period of time. So then, when we're dealing with empirical probability, it's based on the situation that we're in. It's not the same every time. However, there's something called the law of large numbers. Where the empirical comes the classical. And we're not going to do this, but sometimes we can do this. If I gave everybody in the class a die to roll, and you all would roll the die, and then we would count how many ones, how many twos, how many threes, and so on. And then we just keep doing that. And we do it a bunch of different times. The law of large numbers would say each one of those outcomes would have a 1 out of 6 chance of happening. Eventually, our numbers would get close to that, right? But it's not going to be that all the time, right? You could, I mean, if everybody rolls a die, it's not going to divide up equally into 6 different groups. It just, we don't know that it will, because these are variations. These are things that are changing. So the law of large numbers tells us if we have a huge number of people, then hopefully we get closer to, if you want to say, the actual value. The larger the group, the closer we would get to the actual value. But if we're only talking about 30 people, that's not really the answer. But we do have to talk about one other thing, just as an aside. It's called the gambler's fallacy. Let me ask you this question. Why do you think people gamble? Emily, what did you say?
The thrill of it.
The thrill of it. Wow.
The chance of winning.
Are those connected? Do you think that people are more attracted to a low probability thing or a high probability?
Low probability, especially.
Okay, so low probability is actually more attractive to people. They want higher risk in order to get more of a feeling, because that's what it's about, the feeling, right? So, how do people feel if they have lost a number of times in a row? What do they think is going to happen next?
They're closer.
Okay, is that true?
No.
No, it's actually not. Okay, so the gambler's fallacy is not the same as the law of large numbers. It's not true that if you lose a lot of times, then you have to win the next in order to kind of make up for it. That's just not how it works. Okay, but then there's another one. What happens if somebody wins a lot of times in a row?
Don't.
Are they going to keep going?
You think they're winning?
Yeah, they're winning. They're winning, yeah. So either if you lose a lot of times in a row, or if you win a lot of times in a row, you think you're going to win. So it doesn't really make sense. That's why it's called a fallacy. Now, it's also true, though, like if you're in athletics, let's say that a person is really good at basketball, and they get to a point where they hit a lot of shots. They can become more confident, and that can allow them to relax and allow them to actually hit more shots. So the psychological effect in like a sporting event of being really good and of having a lot of success can lead you to even more success, possibly. Or if you're actually not that good, you'll eventually stop doing well and start missing them, and you'll feel horrible. But all right, so these are some psychological effects that we see with regards to this. But then there's a third kind of probability, which is called the subjective or the experiential. What are the chances that I am going to see somebody in the hallway when I walk out?
50-50 chance. Just saying.
Okay, you're just saying, let's try thinking. Okay, so then the thinking person would say, okay, what's going to happen when I walk out this door? Am I going to see anybody?
You might.
Somebody might be, but do you think they will be? What are the chances? Right now, I'm looking at the clock. Is there going to be somebody out there at this time of day?
No, you don't know.
I don't know for sure.
No,
What do I think?
you don't know.
I think no. Nope. All right. If I were to go to the Union Market at 12 o'clock, would I see a bunch of people there?
Right now, it's not open right now.
I know, but 12 o'clock is what I said.
No, it's not open in the summer. Do they-
Yeah, it is.
When did they open up?
Yeah, they're open. Oh, my, you've been missing out here. Yeah, it's open. Yes, it is.
Oh, really?
Yeah, it's open till 1:30. Right? So if I go to the Union Market at 12 o'clock, will I see people?
Yeah.
Will I see people with backpacks?
Yeah.
How did you know that?
Because I've been backpack with me everywhere.
Yeah, and you expect that other people are like you. What are my chances of seeing somebody in a chicken suit?
Zero percent.
Do you think that nobody with a chicken suit would be walking through Western?
It's half in a pig.
Pig costumes? Okay. What if it's Halloween?
100%.
It could happen, right? A few weeks ago, I was up on the north side over by, what is it, Shopko up there, and KFC, and I saw a guy in a chicken suit riding a unicycle on a Sunday afternoon. Okay? Yeah. And I was like, I got to tell my class about that. All right, this is not something you're normally going to see. But I always talk about somebody in a chicken suit. And here I saw a guy, not just in a chicken suit, but riding a unicycle. So, yeah. And it turns out I've seen him more than once. Okay, so he's out there.
So it wasn't the drugs.
No, it's probably for like Rooster Andy's or some place.
Or they have a mattress sale that always stands over there.
Yeah, so there's possibilities here. So then, yeah.
Extra attention.
And so then that's how you know that something is or isn't going to happen more likely or not, because of your experience. You haven't seen a lot of people in chicken suits in the cafeteria, so you say, hey, it's probably not going to happen. What are the chances that you would see 20 people walking down the halls of Western with the same color t-shirt on?
Well, like everyone wears black here, so.
Yeah, it could happen. I'm not worried about that. It could be like the EMTs, right? They have a uniform where they all wear the same color polo or something. So yeah, it could happen. And I've had experience with that. Seeing a bunch of people wearing the same color of shirt. If you had never had that experience, you might not know that. Now, all these three things are all connected. If we say to somebody, how likely is this to happen? Depending on your experience, you might say it is or it isn't. Snow in April, I've seen it half a dozen times. It doesn't affect me at all because I've seen it before. Other people are like, wow, I can't believe that happened, because they just haven't lived as long and experienced the evil of snow in April, right? At the same time, we can't just say, well, it's bound to happen just by chance, because it doesn't snow in July, all right? So you have to have some experience, and you have to have some observations, and you put those together, and you say, I think I know what's going to happen. But probability says you don't actually know what's going to happen. You have an idea of what's going to happen, but you don't actually know the thing. All right. So, yeah. We'll keep going. Just introduce this next topic, all right?
So what's the definition for subjective, experimental, and experiential? Did I miss that?
Experiential, yes. That's based on your experience. Yes, based on experience. Subjective is something that is from the inside of yourself. Okay. Objective is something from the outside. So if it's subjective, that means it's something that I think of based on my own experience. All right. So let's talk about rolling 2 dice.
I was going to ask you what the probability of getting a guess.
We're just about to get there. So I'm going to roll 2 dice. And in this process, one way that we can count up the number of possibilities is what's called a tree diagram. How do we make a tree diagram? We say every choice creates branches on branches. Okay? Now, a tree diagram is not the only thing, right? If you don't get the tree diagram, don't sweat it. You need to understand it more than, I mean, you need to understand how it works, but you don't have to draw it out necessarily. So if I'm going to roll 2 dice, the first die that I roll has 6 possibilities. And that's going to create a set of branches. 1, 2, 3, 4, 5, 6. The second die that I roll is now going to create branches on the branches. So I can have a 1 on the first die, and then the second one creates branches on the branches. And you don't have to go through and write them all down, okay? You have to visualize it in your mind, right? The tree diagram, it has 6 branches, and then each one of those branches has 6 more. So what does this create for us? It creates a multiplication rule. The multiplication says that every decision multiplies the number of results or outcomes. This is why Yahtzee is a relatively complicated game, because you have 5 different dice, and you have a lot of different combinations of things you can come up with. And so every time you think, okay, well, what can happen next? It's multiplying the number of possible things. Okay. So, as it turns out, and I didn't get this until like 3 years ago, the order is always important. When we're talking about this process, the order is always important. A 2 and then a 3 is different from a 3 and then a 2. They are not the same. And certainly you would know that if one of the dice was red and the other one was green, then obviously a 3 on that one and a 2 on the other one would be different. But the fact is, you don't have to paint them different colors. They are different. They are 2 different objects. So when you roll those 2 things, a 3-2 is different from a 2-3. Even if you can't tell the difference between them, they are different things. So order is always important here. And certainly if we wanted to, then we can make a list of all the different things that could happen. So we would have 1, 1, 1, 2, 1, 3, 1, 4, etc. 2, 1, 2, 2, 2, 3, etc. How many do we get? 36. 6 times 6. We had 6 options, and then we had 6 put on top of those. So that gives us 36 different options. So then if we say, what's the probability of getting 2 5s. There's only one way for that to happen, and that would be both of them to be 5, so that'd be 1 out of 36.
But couldn't that be 2 out of 36? Because that could be, oh, wait,
Nope.
or it doesn't matter.
Yeah, because they're both the same. So, okay, what's that decimal number? 1 divided by 30.
.0277.
Okay, so now with probabilities, there's a lot of times we would go out to like 4 decimal places. We call it 0.0278. Is that unusual? Why? So this is less than 5%. So if you're rolling 2 dice and you say, I have to get that to happen, you will be surprised if it happens. 1 die, no. But to get 2 dice to come up to be exactly what you want it to be would be an unusual thing. And I haven't figured it out yet. But I was playing a game where we were supposed to roll the dice to know who went first. All 4 of us got double 1s when we rolled it. So that was crazy. I haven't figured that out yet, but I could. But let's do Yahtzee. What would be the chances of getting 5 dice to all come up to be the same? Well, you could have 1, 1, 1, 1, 1, right? Or 2, 2, 2, 2, 2. 6, 6, 6, 6, 6. There are 6 of these. 6 Yahtzee. How do we get the number of total possibilities?
6 to the 5th.
6 times itself 5 times. And so we would write that 6 to the 5th power. So this is 1 divided by 6 to the 4th. All right, so what I want you to do is I want you to get this on your calculator. I want you to make this happen.
Why did it switch?
Why did this become that?
Yeah.
I divided 6 out of the top. 6 divided by 6 is 1. This has 5 6s, now it just has 4. So,
Why? Because I don't understand.
okay, if in order to reduce something like 9 over 30, I divide top and bottom by the same number. Okay? I had 5 6s down the bottom.
Well, so maybe it's a power, but then divided by 1 of them, so there's some less.
That's correct.
Sorry.
That's all right. That's what they call a smart question. Okay? It's not a dumb question. It's a smart question. Okay, so I want to know on your calculator, how are you going to do 1 over 6 to the 4th power? You need to know how to run your exponent key. Make that happen. Okay, you know what's the exponent key. And you need to take the order of operations. Your calculator should be able to figure that out. 1 divided by 6 to the 4th. And hopefully you'll get the right answer if you do that. 1 divided by 6. Ooh, where's my scientific thing? 1 divided by 6 to the 4th power. Now, your calculator might go into scientific notation. Okay? If it says 7.7 e negative 4, does anybody have that on your calculator? 7.7 e negative 4? Good. So what you should have then would be 0.00077. Done. That. Okay. Okay. Sure.
Thank you.
Your exponent key either looks like this, or like that, or like that, generally. And sometimes they're not easy to find.
It's good enough.
Yeah, it's a-
Thank you.
Oh.
So then you would have 1 divided by 6, and then your x to the y key or whatever, 4 equals 6. Should come out of that.
So you want to do 6 to the 4th first and then divide?
You could say, here's 6 to the 4th, find that number, and then take 1 divided by that number. That would also work. Yeah. Yeah, your calculator understands the correct order of operations for that kind of thing.
We have a calculator today, so.
Oh, okay, yeah, well, all right, yeah. Using your brain, that's good.
Mr. Powers,
Yeah.
how did you use the tree then
To get
the
that.
numbers
Okay.
here?
Every decision multiplies the number of outcomes.
Okay,
So that means for the first die, it's 6 things.
right.
For the second one, it's 6 things.
Yeah.
The third one is 6. So I had a Yahtzee, and I didn't explain the rules of Yahtzee, sorry. But you're supposed to get 5 dice to all come out the same.
Okay,
So if you have 5 different dice, each one of those multiplies 6 in terms of the number of possibilities.
okay,
So if I just roll 1 die, it's 6. 2 dice, 6 times 6. 3 dice, and so on.
got it.
So then this is 5, 6 times itself, 5 times. And then when I say, how many outcomes am I considering? How many ways can I get a Yahtzee? These are the 6 different ways. So that's 6 on top. And then this.
Okay. Okay.
All right? So once again, that's a good question, all right? That's the right kind of question. All right. So, Natasha, how likely is it that somebody can get a Yahtzee on just 1 roll of the dice?
I have no idea.
Okay, but if we were to look on here and we were to say, hey, there's a small decimal number up here and it's 0.00077.
Very unlikely.
Very unlikely, okay? So in percentage terms, Emily, what did you say it was? 0.08.
Oh, you want to scroll down.
Okay, you got to remember how to round those things out. Okay. Okay, so this is your chance to practice. 0.08%, which is very low. All right. What's this number 6 to the 4th power? 1296? So you would kind of think that this thing would only happen once every 1,300 times you roll those dice. Now that means they all have to happen at once. In the rules of the game, you can make it happen with 3 different rolls, and that gets complicated. But in order for you to get a Yahtzee, just by rolling the dice 1 time, you would expect that once every 1,300 times you roll it. Now, if you play a lot of Yahtzee, that could happen. It's not impossible. I've seen it a few times. I've played a lot of Yahtzee in my day. So yeah, it can happen, but it's certainly unlikely to happen. Yet, if I were to play Yahtzee, 4 hours a day for 20 years, sure, I would kind of expect this to happen once in a while. All right. Let me just back up though. This is really important for you to understand. You're not going to understand this stuff right away. Okay? What we're talking about are things that people don't talk about generally. This is a way of thinking about how things happen that people have struggled with for hundreds of years. The first people who created this stuff, when they did it at the beginning, they got it wrong because they didn't know how to count things properly. What I'm sharing with you is things that people have thought about for hundreds of years, and not everybody gets it right. In fact, a lot of really smart people struggle with the whole concept of probability. And that's okay because struggle is, the bumps are what you climb on or whatever. So it's okay for you to not understand this and not get it completely. As long as you don't stop, okay? As long as you say, well, I don't understand, I don't know exactly why I'm doing this, but the teacher said I had to. That's the right attitude, okay? Just do the thing. You don't have to understand it right away. That'll come after time. Okay, so let's take a break for 10 minutes. 4:10. And then we'll come back and we'll figure the rest of this out.
Oh, so then be like, yeah.
So how are we doing over here?
Oh, just like the number.
C'est la vie. Okay.
I would never.
What I'm finding with mine.
My expenses have this. calculator.
Yes.
Okay.
That's this here.
Oh, wait.
Okay.
I don't know if that is.
Right? What does that actually mean?
That's one I was.
It means I take this number, 7.7, and I move the decimal 4 places. So when you see this number, that means it's small, it's actually a small thing. And then you put 3 zeros in front. Instead of 4, you put 3 zeros in front. Now, I can set
I
this.
was worried about when I started thinking, like, they're like, oh, you know, like, turns out to the, like, you know, it's like, right now, like, oh, all of a sudden, we have the clients that get discharged, and now I have to pick up another client that needs time, and like, this is like, sometimes, like, but I'm just like, this is how they, like, you want it, but I was like, oh, I'll make it up by Friday.
Everything else is gonna be.
Right. Because, all right. So I've got the TI-84 plus okay. Ah, here we go. Okay, so. Okay. The mode settings and the size of the number. Okay. Okay, let's see if I can get more with this. Okay, let's try this. Scientific notation. Small number.
Yeah, they're in that desk out. It's literally like my time.
Okay.
You can move it last time.
Okay. TI plus scientific notation. Specifications. Okay, let's try this. No, that doesn't look right. Hardware, built-in functionality. Okay.
No.
So is this the same thing? No, it's just getting started. Okay, that's not what I want. I want the guidebook. All right, there we go. So this is what I want. Guidebook. Haha, there we go. Default. Talk is not my default. Okay.
I've had conversations.
Following pages. Default is. Oh. No.
That's
No.
way different.
Default is.
Default
Yes.
That's hard. Like I would have a hard time with that.
Default for lower, default for upper. Random.
Look at this guy.
Okay.
She's gonna get it.
Okay. There's the graph mode. Explain the window variables. And graph format. Style. Okay, how far are we? Oh, 108. Yeesh. Let's go for scientific
Okay, just go to down.
notation.
Oh, that's nice.
Okay. Okay. Huh. I can't fix that for you.
No.
So, and that's what you'll have to do then, because you'll see that happen. You know, if I go 1 divided by 2,000, it does the same thing. If I have 1 divided by 200, it does that. But if it's smaller than that, if it has 3 zeros in front of it, then it makes it different. So, yeah. So if it has a -4, you put 3 zeros in front. If it has a -5, you put 4 zeros in front.
Okay.
Does that make sense?
Yeah.
Okay. All right. Here you go.
Yeah.
We don't talk about this.
Then would that be one of
A week after. I'll be back next summer. Yeah.
So maybe there's a select few review and
That's
throw you guys down.
You know what you want to do.
That's stressful.
No? I mean, I didn't even think it would be faster. Yeah. Yeah, I get along. Oh my God, you know, she
You guys did really
Wouldn't it be horrible if, yeah, there was only like 2 or 3 people that got this far and it's like me.
Even that, my girls didn't know. And I think that's like my big worry is.
She said that she works.
Well, that's my main girl.
Yeah, that's too bad. Oh, well.
They don't cover their shift. And she said,
So.
yeah, I didn't think I'd even get it.
Oh, that is weird. Did you say that financial statement, which is due?
Wait, do what? No, it shows like what we're getting charged for fall, what we have to.
Oh, what we're gonna go.
Is it less than your estimated cost?
So like I figured, yeah, every layer, every time we work on it.
Crazy, man.
Mine did not.
I got 7,500.
All right, so we'll start back up here.
My parents might see.
So there's a couple of things that I want to just mention before we get further into the idea of the tree diagram. The basic idea here is what's called a complement rule. Complement rule, complement here is something which completes. That's something that's not one thing, but something else, okay? So let's say that the probability of rain is 80%. The question would be, what's the probability of not rain? So the probability of rain is 80%. What's the probability of not rain? Aaron? 20%. Okay. Now, why do you think that's true, Aaron? Because they have to add up to 100, right? Because either it's raining or it's not. Okay? So, this is something which is kind of a basic definition that doesn't always work. Okay? If you say, either I'm happy or I'm not, well, I can be happy and other things at the same time, right? So then, you know, it doesn't always work for everything. But in probability, we say that it does. So that we can have only two things happening. Either something or not the thing. Okay? Now, when you say they have to add up to 100%, which is correct, the formula does not use percentages. The formula uses decimals. And this is something that happens a lot. The formula is going to use decimals. Okay? So when we have a formula in probability, most of the time, it's not talking about the percent number, but the number expressed as a decimal number. So we say the probability of not A is equal to 1 minus the probability of A. Okay? So then what would that look like here? We're talking about the probability of rain is 80%. What's that as a decimal number then? Sorry, what did you say?
0.80.
0.80. So then, if I take 1 minus 0.80, I'm going to get 0.20. So this is how these formulas work. You're going to be putting in decimal numbers in order to make the thing happen. So you have to be really clear about what's the connection between percents and decimals. 80%, 0.8. 1 minus 0.8, 0.2. 0.2 as a percent, 20%. Okay, so that's how that thing has to work. So that's the complement rule, just something to bear in mind. Now, when we get to this multiplication rule, which we have here, every decision multiply the number of outcomes. So let's go to the cafeteria. And I want to get a sandwich, a snack, and a drink. And my question is, how many options are there?
Depends on how many choices you have for each.
That's correct. So let's think about it. How many different sandwiches could you get? We're not talking subs, okay? Subs would go nuts. But let's just talk sandwiches. I'm going to walk into the cafeteria. I'm going to buy a sandwich. How many possible sandwiches might I have? $3,000, 2, probably a number in between there. Okay, what do you think?
Turkey, ham, and salad.
Turkey, ham, tuna salad. Now we're talking summertime. If it was the fall, right, you'd have all those different burgers and everything, but they're not doing that right now. So let's say we have 3 sandwiches. How many kinds of snack?
Are you talking chips? Or
I am talking chips. How many chips do they? How many different kinds of chips? 5. What other kinds of snack could you get? Cookies, fruit, muffins, yogurt, soup. How many options are we up to here? 3,000?
Let's just say 15.
Let's say 30.
Okay.
Because you have, what, 6 different kinds of muffins, 8 different kinds of cookies, 5 different kinds of chips, how many different kinds of yogurt, anything else that might qualify as a snack. Okay? How many drink options are there? I'm sorry, what did you say?
Water, soda.
How many different sodas are there? Maybe 8, because they're different on the other side. So we got water, we got 8 sodas. Coffee, how many kinds of coffee are there? Okay, 2 maybe. How many teas can you have? How many kinds of milk are there? How many juices are there?
Let's say 30 again.
Let's say 30 again, all right? Okay, what's that number? $2,700. Now, I have various family members that have had various struggles with mental health issues over their lives. And one thing that happens with mental health is that you have people who are convinced that there's only one right answer. So they walk into a cafeteria and they say, I need to decide which sandwich goes the best with which snack and which drink. And I have to think through all those possibilities because I don't want to make a wrong choice. And they have to think about all those different choices. How long is it going to take them to order?
So as long as we.
Yeah, all right, there you go. About as long as you, okay. Because they have to think through all 2,700 of these options before they can decide which is the actual right thing. And in fact, a lot of times somebody would walk into a situation like that and they would say, I can't do this. I can't think through all 2,700. How am I going to know if the orange juice or the cranberry juice goes better with the Dorito Ranch chips when I have the turkey? How do I know which one? Yeah. Most of us don't do this. Most of us do not think through the entire 2,700 options. Most of us just go in there and get something we like, and it's okay. And most of us hardly ever think about doing anything other than the thing we've always done. The usual. We just get the usual all the time. Most of it. But when you start to think about what actually happens here, you're talking about a huge mental exercise that people have to go through sometimes. Now, let's just consider the fact that if you are going to, let's say, be in charge of the cafeteria, and you want to know what are the different options, and you're creating more options, you have to ask that question. Am I creating options that people are going to actually like? And so I don't think you're going to think through all 2,700 of those. But you got to have in your mind at least what's going to happen if somebody gets this snack with this drink. And if you're a nutritionist, you got to think about how many calories and how you're trading those things off, not to mention the vitamins and everything else, with all 2,700 of these options to say, I'm going to recommend that you not get this snack with this juice and this sandwich, but whatever. Okay? All right, well, there's more we could talk about here, but we're going to leave that for now. All right, so now we're going to talk about getting a box of light bulbs. I have 6 light bulbs in a box.
One of the Menards.
No, I'm not going to Menards. How many do if I go to Menards, how many are in a box?
You can get 12 left.
You can't get 6?
Well, you can, but.
All right, well, that's what I want. I want 6 in a box. But for whatever reason, 2 are bad and 4 are good. Okay? And what's going to happen here is I'm going to take out 2 light bulbs, and I want to know what are the different things that can happen. I am taking them out yet, man. I do not know which ones are bad and which ones are good. So I'm just going to pick 2 of them. Well, then the question is, what happens? And what are the probabilities associated with the different things that can happen? Okay? Now, it's possible for you to do this using a tree diagram. It's also possible for you to do this just based on thinking through the process. Okay? So, if we use a tree diagram, then that would be a way for us to organize our thinking so that we can see exactly what's happening. For some people, it's too much information and they just get lost. Okay? So we're going to try it without the tree diagram first. And then we're going to try it with the tree diagram. Okay. So I want to know the number of possibilities that can happen. If I take out 2 bulbs, it's possible that I could get a good bulb on the first try and a good bulb on the second try. That's possible, right? I could get a good bulb and then a bad one. I could also do what else? I could do a bad and a good one, or both of them could be bad. Okay. Now, as it turns out, these 4 things are not equally likely. We're talking about classical probability here. These things that I have listed are not 4 equal possible outcomes. Each bulb being taken, that's equally likely. But these 4 things are not equally Okay? So the first question is, for that first bowl, when I open up the box, how many possibilities do I have of getting a good one? When I look at the box, there are 4 good ones, right? So that would go here. This would be 4. This would also be 4. How many bad ones when I open the box? 2, 2. Right? So when I open the box, I see 4 good ones. But again, every decision multiplies the number of outcomes. After I grab that good bulb, how many good bulbs do I have left?
3.
3. So then I would multiply this times 3. I have 4 good ones, and then after I take that one out, I don't have 4, I only have 3. So then, how many possible ways can this happen? The answer is 12. And multiply the possibilities. There are 12 outcomes for good and good. There's 12 different ways for that to happen. Now there's different ways you can think about this, and it can get really complicated if you want it to. You could say, well, the ones that are good, let's label them G1, 2, 3, and 4. So G1, G2, G3, G4. And then you can go nuts and write down all the different possibilities. We're not going to do that. We're just thinking through the possibilities. Now, if I have a good bulb and there's 4 good ones, I take one good one out, how many bad ones are in the box? There are still 2. After I take out a good one, I still have 2 bad ones left. So this is 4 times 2. It would be 8. Good, comma, bad. What happens for the bad, comma, good? I started with 2 bad ones. I took 1 bad one out. I still have 4 good ones. 4, which is also 8. Bad and good. Now what about the bad and then the bad? I had 2 bad ones. I took 1 out. How many do I have left? 1. One of those, 2 ways for that. So I want to know what's my probability of getting 2 good bulbs. Good. What is my total number of outcomes? 30. How'd you get that?
Added all the outcomes.
If you add up all the outcomes, you get the number 30. 30 total outcomes here. So the probability of having a good and a good would be 12 divided by 30, which is what? 0.4 or 40%. Now, once again, most people have never done this. It's okay, but it's a way for you to think through the process in order to know what can happen. You don't know what's going to happen, but now what we're doing is we're figuring out what are the possibilities and how likely are they to happen. So, I've got a box. I know I've got bad bulbs in it. Is it possible for me to get 2 good ones out there? Would I be surprised to get 2 bulbs out of there that are good? No. 40%? Would I be surprised if I had something bad happen? I would not be surprised, okay? It's in between. It could happen that I'm going to get 2 good ones, but it certainly might not happen. What about getting both of those bad bulbs? What's that going to be? Emily Grenier, you got a number?
7%.
7%. How'd you get that number?
I took 2, divided it by 30, and I got 0.06667.
Which is about 7%. So I'm looking at this box. I've got 6 bulbs in it. 2 of them are bad. What are the chances that I'm going to get both bad ones? Well, it could happen. I would not be surprised. I'd be kind of surprised, maybe, right? Now, you can think about this in so many different situations, right? Let's say you have 300 kids on a playground. What are the chances that if you just had 5 kids playing on a piece of equipment, that all of them would have issues of balance? Well, I don't know. What are the chances? Could you have it happen? Well, maybe it could. So then you've got a certain amount of equipment, and everybody that's on there is not going to be very balanced or coordinated, and so they're going to run into each other and cause a huge problem. I don't know how this works, but it could happen. How likely is it for it to happen? This would be something you'd be able to figure out, knowing what % of your children have trouble in a certain way or whatever else, right? So this kind of idea is kind of where we start. Now I want to show you what the tree diagram looks like. Some people find it helpful. It would look like this. For the first bulb, I would have 4 and 2. 4 good, 2 bad. For the second bulb, I'd have 3 good and 2 bad. And here I'd have 4 good. So this would be a way, using the tree diagram, to kind of show what we did with these numbers. The first time we opened the box, we had 6 light bulbs in it, and we figure out what's going to happen. Then after we take out one of the bulbs, we would have different scenarios. The 3 and the 2, or the 4 and the 1, depending on what we did. So I'm not going to require you necessarily to make a tree diagram. If you can figure it out either way, that's okay. So let's do another one here. See if we can make this work. So let's say I have a box and in this box I have I have 6, so let's make it 8. I have 8 socks in the box. And I have 3 that are red and 5 that are. And I'm going to ask the question, what is the probability of getting, I'm going to take out 2. And what is the probability of getting a match? All right, I'll give you a couple minutes, see if you can figure this out.
So the 3 red and the 3 blue, those are not matched pairs already?
Okay, I've got 8 socks in a box. They're not matched up at all. I have 8 individual socks. 3 red ones, 5 blue ones. I'm going to take out 1 sock, and then I'm going to take out another one. And I want to know what's the probability that that pair of socks is matching.
Well, the probability of both the blue and the red pair, or just the probability of matching them?
Either possible.
One, choose one.
Either one would be matching. All right, so we're going to make it a group project now. You can get help from your neighbors, and you can help your neighbors. See if you have what they have, see if everybody's right. Okay, what that means is I want you to actually look at somebody else's paper, okay, and talk to them about it. Maybe include more than one person. You got other people you can talk to. But I want you to talk to somebody else at least, or maybe 2 people. See if they have the same thing you have. Now, I could call security and throw you at each other, but I don't really want to do that.
So then you would be.
Yes, yeah, you can go around here.
This one, we have 3 residents.
So we want to know, like, what this one is. He just had a mess.
20 times. Yeah. I think. No, it's like if you take progress off of that. And that's 2 sides.
Okay, Alyssa Cooper, can you tell me what's going on here and how you're going to figure it out?
Which one do you want to know?
I want to know the answer.
Okay, so we did it where like we solved for the probability red and blue and then we add together.
Okay, so tell me what that looks like here.
So for the probability of the red match, we came with 11%.
How did you get that number?
Because you divide 6 by 56.
Okay, how did you get 6 and how did you get 56?
Because if you pull out one, or the first time you have the opportunity to pull out 3 red socks, the second time you would have the opportunity to pull out 2, considering you already pulled one out. 3 times 2 is 6.
Okay,
And then if you want me to go through the whole thing?
I want to know where that 56 came from.
Okay. So if you do a red and a blue,
Okay, hang on. There's a shorter way to get that answer. Okay. The first time I was taking out socks, there were 8 of them. The second time I was taking out socks, there were 7. So this would be 3 out of 8, 2 out of 7.
that's how I got 56.
Okay, that's not how you got it, but that's how I got it, and that works, okay? So that would be 6 out of 56. All right, so Alyssa, tell me about the other one.
For the blue one, first time you pull it out, there'd be 5. Second time, there would be 4. So you get 20.
Okay,
Instead of 56.
and it's still 56. It's 5 out of 8, 4 out of 7. And it is true that if you do, and this is blue and blue, if you do red, blue, that would be 3 times 5, and blue, red would be 5 times 3. So if you add those together, 15, 15, 20, and 6, you would also get 56 that way. Also works. But it is true that if you just look at what's happening, the first time there's 8 possibilities, the second time there are 7 possibilities. So 8 times 7 is 56. That's what you get. So then you have 26 divided by 56. What's that number, Liz?
But, where'd you get 26?
0.464.
464, so
Okay.
46%.
46%, more or less. There's 6 red combinations that match. There's 20 blue combinations that match. So there's 26 matching combinations. So that's 26 out of 36.
So, but if I did it like the long way, and I got 36 for the, like 36% for the blue and 11% for the red pair and added them together, you get 47.
Okay,
Is that?
is that a problem?
I mean, it's way.
Okay, what do you think?
I hope not.
You hope not.
Yeah.
You're right, okay? Because your process was good. And when you round off numbers in the beginning of the process, sometimes when you come to the end, it's not exactly the same thing, right? And in this situation, that's not a huge problem. However, later on, what you might want to do is not round those numbers off at the beginning. So it's not exactly 11, it's not exactly 14 or 35. Okay? So I guess I would recommend not rounding off until you get to that. Now, I do want to kind of show you what it looks like if you do the tree diagram. You'd have 3 red, 5 blue. And then here, if you take out a red, you now have 2 red, 5 blue. If you take out a blue, you still have 3 red, and 4 blue. That's what your tree diagram would look like. It's not absolutely necessary though, because you can look at the numbers and just think of it like this.
Which way would you prefer us to do that?
It doesn't matter.
Okay.
Either way is fine.
I did this way because that's what we showed in the previous example.
Either way is fine. You can do it this way by just looking at the numbers and multiplying things together and then adding. Or you can do it using the tree diagram and write down all the possibilities. Okay. Now, generally speaking, once again, people have never seen this before, they've never done it before, and it feels unusual to them, and they get confused and feel frustrated. That's normal, okay? The fact is, if you can do it, that's good. And then it makes more sense to you later, which is okay. Doesn't have to make complete sense right away, but it will need to make sense down the road when we do other things, which we'll move on to shortly. But Natasha has questions.
Just because I now do it otherwise, how would you get your percentages from the tree diagram?
So then you would multiply as you go across. So it's 6, 15, 15, 24. And then you would say 6, no, 20, I'm sorry. So then you say these are the ones where you have matching here and here. So then that'd be 26. And if you add them all up, it's 56. So, all right. So what's happening here right now is that we have, if you want to say, demonstrated a specific principle in probability. And that is that you multiply the number of options, right? So then I multiply the number of options on the top of this fraction. I also multiply the number of options on the bottom of this fraction. But as it turns out, this is a probability, and so is this. The probability of getting a red sock is 3 divided by 8. After I take out one probability, or one sock, then this changes the probability to 2 out of 7. And so what we have to look at is, what does this actually reflect? What does it mean when I take 2 probabilities and multiply?
If you were to do the tree diagram,
Yes?
how do you get your fractions or? how do
Yep. That's a great question, and this is how you do it. You look at this, this is 3 and 5, but they are out of 8. So then I just make this 3 out of 8. And then this is 2 out of 7. So, okay. So when I'm thinking about the process here, I am actually multiplying probabilities, and I use the word and. And this has a specific meaning in probability, and that is both at the same time. What does it mean that I have red and red in my hand? It means the first one was red, and the second one was red. I look at them, they're both red. That's red and red. I'm looking at them and they are both red. Okay, that's what we mean by and. So then the mathematical formula here is probability of A and B is equal to the probability of A multiplied by, and we use a dot for that, probability of B. It means multiply. Now, this is not any different than what we just did. What we just did was multiply. We multiplied 3 times 2 to get 6. We multiplied 8 times 7 to get 56. It's the same thing, it's just written in a different way. That's all. So then when we say, how does this work? This is the idea of having a matching pair when we multiply. Now this situation would also happen if, for example, you're in your doctor's office, okay? And we'll take this out right now. Or even at the daycare or whatever. My daughter works in daycare, so that's how I think about it all the time. So let's say that the probability of having a child with the flu, and we're talking not necessarily that they are sick with the flu, but that they have it, right? They don't have to be sick and still have it in their system, right? So let's say the probability that the child has the flu is 20%. Now it's important for you to understand what this is talking about. This is what's called the general probability. I'm giving you this. I'm saying to you that out of all the kids in the world, or in lacrosse or whatever, the probability of any one child having the flu is 20%. If I just pick somebody at random, 20% of the time they're going to be flu-ridden children, okay? So then I'm giving you that as a general probability, and then I ask the question, if I have, let's say, 4 kids in a room, I want to know what's the probability that they are all sick. So I'm thinking about these children. They're sitting here. I got 4 of them. I know that generally 20% of the kids out there are sick. What are my chances that all 4 of these are sick children and they have flu in their system? Now, I'm going to show you the tree diagram, and then you don't have to really think clearly about it, but you have to think how it applies, okay? For the first child to be sick, there's 20% chance of them being sick. There's an 80% chance that they are not. Every time I think about an additional child, I'm going to create branches on the branches. So what about that second child? Once again, 20% sick, 80% not on each of those branches. So I'm putting branches on the branches, which I'm supposed to do. I have another child who's creating new options. I'm not going to make the entire thing here. I just want to think about all 4 of them being sick. So that would be this one is also sick, and this one is also sick. And the rule tells me I can multiply these probabilities. If I want to know what is the chance that all of these children are sick, I'm going to multiply these probabilities together. How would I do that on my calculator?
Why didn't you put that last one down at the bottom?
Because they're sick. Sick goes up, not
There's only
sick goes down.
4.
And there's 4 children. Here's the
What,
first
4 on the
child.
not sick part?
Here's the second child. Here's the third child. Here's the 4th child. I could have made the rest of the thing all the way down here with all the branches.
So you have 4 on the bottom too, right?
I would have all of these here, and then I would have more here. Every time I do it, I add 2 more branches on each branch. Like this. Like this, and this, and this, and this, and this, and this. There, does that make sense?
No.
Okay. Every time I look at a child, it creates a new set of possibilities. I put branches on the branches. Every child has a 20% chance of being sick and an 80% chance of not being sick. This is the first child, this is the second child, this is the third child, this is the 4th child.
What's the easy one?
We'll get there in just a second. All right? My question here right now is, what do I need to do with these numbers? As I go from one branch to the other, what do I do with the probabilities? I multiply them. So I'm going to be multiplying the numbers as I go down here. So then the easy way is to consider what happens if I take 0.20 and I multiply it by itself 4 times. How would you do that on your calculator? To the 4th power. 0.20 to the 4th power. What's that number? So if I have 4 children, there's a 20% chance that any one of them is sick. It's not likely that all 4 of them are sick. Okay, that's just not likely to happen.
So the probability percent would be what?
Why does the tree
Two and that one, 2?
0.2% would be the percentage. Yes, it would be. Okay? Now, right now I'm showing you this in terms of the tree diagram because this is illustrating for you how many different options there are. There's a lot of different options. The only one I'm concerned about right now is that all of them are sick. I'm now going to consider the possibility that none of them are sick. If none of them are sick, how would I get that in? I would take 0.8 to the fourth power. What's that number? What percent would that be? 41%. So is that going to happen most of the time? Something that happens 41% of the time, is that most of the time? No. Now this is a little bit advanced, but I'm gonna put it on you here. See if we can make it think. Right? What's the probability that someone is sick? And again, this is a little bit advanced, but if you ask the question, what's the opposite of nobody? Sorry, not
Someone.
somebody. Is nobody coming to the party? No, somebody's coming to the party. Okay. So the opposite of nobody would be somebody. So this would be 59%.
Oh.
Are they all well? Are all these children healthy? If the answer is no, that's the opposite of them all being well. So the opposite of nobody is somebody. Okay, so there's a thing. All right. Now, as it turns out, I have 8 more minutes. We have another topic that we're going to do in these next 8 minutes. It's related to just what we just did. And as it turns out, it's on your homework. So it's probably a good idea for you to know how to do this. This is not a tree diagram. This is what we call a contingency table. This is something you'll see a lot. And we're going to put numbers in there. I want to know how many total people I talk to. I talked to a number of people. I asked them what soft drink they preferred, and I asked them what program they were in. How many total people did I talk to? 200. How'd you get that?
I added them all.
Add them all up. 200 people. What's the probability of being a Coke drinker? It is 50 over 200. How'd you get the 50?
And the nursing students, the business.
Add them up, right? So this would be 50, this is 70, this is 80. This is 60, this is 140. Probability of being a Coke drinker would be 50 out of 200. What's that number? 25%. What's the probability of being a business student?
Being a business student.
140.
140 out of 200. What's that? 70%. Now, all those years when people said to you, it doesn't matter if you do it on your calculator, if you do it in your head, it does. If you're able to look at this and see, oh, 140 divided by 200, yeah, that's 0.7, yeah, that's 70%. Generally, that's easier if you can make it happen in your head, but if you're able to use your calculator, that's good. For you to not even think about it and say, well, I guess somebody else is going to get it right, that might be where you are, and that's okay. So then, the question that we have here now, though, this does not work like a tree diagram. What we were doing with the tree diagram and this multiplication over here, that does not work here.
Should, because this is easier.
Yeah, it's quite easy anyway. Because if we say, what's the probability of being a business major and a Coke fan, what we look for is the overlap of those categories. So how many people are business majors and Coke drinkers? 40. Out of 200. $20. So as it turns out, if we multiply these two numbers together, it does not come out to be 20. And that's important for us. As it turns out, this will tell us something. It tells us that business students have less desire for Coke than what we would expect from them. Okay? If we multiply them together, that would be like a tree diagram, but there's something else happening here. And so then that's something that we need to know, not right away, but down the road, we will be able to say, and that makes a difference. This specifically, this is how Facebook and Google and everything else happens on the web. Are you a Brewers fan? Then you're more likely to buy this product than somebody who's not. So that's how all this works. You put people into categories, and then you decide, does that affect their behavior? Does that change their decision? Does that make them get better when you treat them with acupuncture or whatever? So we'll do that later. Oh, have a good weekend.
Mine's a 0. And I know for a fact that we got like $10,000 between. Or, well, no, 75 for that, like, we have the financial need or whatever. But it didn't, whatever I saw in there didn't tell me the scholarships or anything.
Yeah, mine had my scholarships on there and then.
Maybe they're just working on updating.
Yeah.